Taylor, and this is my lab report for Lab 4 Oscillations. Here's the table of contents. The purpose of this lab is to determine the period of oscillation of a 2D spring mass system, generate a computer model of the system, compare the two systems, and test the energy principle using the computational system. The models used to do so are both physical with the spring mass system and computational with the same spring mass system. The lab successfully compares the two systems by proving the energy principle true, but a physical period of oscillation could not confidently be determined. Relevant equations and principles, we're going to need Newton's second law, which states that the net force on a system is equal to its change in momentum over change in time. That can be derived to become the velocity update formula, which will be used in the code, as will the position update formula. The force of a spring, the potential energy of a spring, the change in potential energy of gravity, and the force of gravity are also going to be necessary in the coding. And the energy principle states that in a closed system, the change in energy of the system is zero. So we use a physical model of an oscillating spring mass system analyzed via tracker, and the mass is the system, everything else is the surroundings. A computational model of the physical system in GlowScript is used, and then a computational model of the spring mass system in GlowScript is used where the spring, the mass, and the earth are all a part of the system, and there are assumed to be no outer surroundings. So for the experiment, the video of the physical spring mass system was provided and analyzed via tracker. Its motion begins from rest, and the mass, spring constant, and relaxed spring length are known. The X and Y positions of the mass over time were recorded and put into a CSV file to be modeled later in GlowScript. So here is the video in tracker. We have the origin at the spring attachment point, the length scale set from the spring attachment point to the center of mass initially of the mass hanging down, and then we track the motion of the oscillating spring system. Its X and Y positions are generated, as well as graphs of its X and Y positions over time. This X and Y data was put into the spreadsheet that was converted to a .csv file so that we could use it in the code later. The spring mass system was released from rest. For the coding, we use the Lab 4 starter code and edit specific lines of code to input initial conditions and apply the active forces on the system. Keep track of the energy values and changes of the system over time, and input the CSV file to show the computed system versus the real system and graph the modeled system's energy. So here's the code. We input the ball's mass, its initial position before it's released from rest. Put in the spring constant, the relaxed length, compute the system's energies, compute the changes in all of these quantities as the system moves. When we put in the CSV file, we're able to see in blue the computed spring mass system, and in red the experimental physical spring mass system. You can see that overall they're pretty close together, but there are some slight differences. The red spring mass system seems to be oscillating in a slightly different trajectory than the computed blue spring mass system. The code generates a graph of the system's change in energy versus time, and it compares the X positions and Y positions versus time of the modeled and experimental systems. So here is that energy graph, and here are the positions of the model and experimental systems. Sources of error would have been imperfect physical tracking in tracker and improper assumptions. So maybe there was some initial velocity imparted on the physical system. For the modeled system, the energy principle is satisfied as the change in total energy of the closed system is zero. We can see that as the orange delta E graph is zero the whole time. And in the real system, the change in energy would not have been zero because it was exposed to air resistance, damping, and other possible outside forces that would take energy out of the system. The X and Y positions of the system were used to calculate the period of the oscillations, and there was a period generated for the X using the X graph and a period generated using the Y graph. The periods are slightly different, and it's too different to be considered the same. Damping has more of an effect in the y direction when you look at these graphs, but the period is independent of position, so that really shouldn't make an effect on the period difference. So a true period cannot be determined. Energy is always conserved, but it only stays fully in the closed computational model. The real system experiences damping and air resistance, and the system has differing periods in the x and y directions. Thank you.